and he realized that that there must be some very dense, very heavy, very massive components of an atom that could kick back alpha particles. And so he invented this concept of the nucleus, you know, the core of the atom, very heavy. Most of the mass of an atom is contained in the core, or the nucleus of the atom, right? So then he dreamt up this new model of the atom that was at the center was a very heavy, massive nucleus, and the electrons were circling the nucleus rather in the way of a solar system, the way the planets orbit the sun. So for the atom, the sun was the equivalent of the sun would be the nucleus, and the equivalent of the planets would be the electrons. But there was a problem, conceptual problem. These electrons, if they're orbiting, you know, going in circles, that means they're accelerating, and therefore by Maxwell's electromagnetic wave theory, that means that those electrons should be radiating electromagnetic waves. And electromagnetic waves have energy, energy is conserved, therefore the energy of the electrons should get less, and then they should spiral in, you know, less and less energy, they should spiral into the nucleus. And you can calculate, you know, with classical models how much time it would take for this to happen. You know, it's a tiny fraction of a second. So obviously something's wrong, because atoms are stable, right? And, you know, this book continues to exist, this pen, right? Atoms are stable, they don't snuff out. So what's wrong? So, you know, so the electrons should spiral into the nucleus, but they're stable. Well, why? Why are they stable? So there's a deep problem here. And this is the sort of question that Niels Bohr was asking himself around early 1910s. Okay. Another mystery was if you take metals and you put a little piece of metal in a Bunsen burner, you know, a very hot flame, it will emit specific colors. Like if you put copper and you put it into the Bunsen flame, you'll see green light coming out, and so on. In fact, if you put that light through a prism and you split the light up into its various frequencies, each atom has characteristic frequencies of light that it emits. Not continuous, discrete, right? Again, quantized, and and there were interesting numerical relations. You know, mathematical physicists were finding formula for the numerical formula for the frequency values of the light coming out of these heated elements, these heated atoms. But nobody understood why. Why did they take the values that they do? You know, the frequencies of the light coming out of the atoms. Why? Where did all that come from? Why? No one knew. And then Bohr comes out and made himself famous with a theorem. He's saying that I think it was around 1913 or so. His model, his new model, he took Rutherford's model with the nucleus at the center, with electrons orbiting the nucleus, but he said that these electrons can only have quantized energy. They can only have certain orbits. They can't have any orbit, only certain discrete orbits around the nucleus. That was his model, that was his theory. And the energy that these electrons could have was proportional to 1 over n squared. N is just an integer, right? So here's the nucleus, here's one orbit of an electron, here's another one, and the energy of that orbit is proportional to 1 over some integer squared. And Bohr's model was, using Einstein's ideas for photons, he said, if an electron jumps from one orbit, say an outer orbit, into an inner orbit, then that energy difference, like the if the energy of an orbit, an electron orbit going around the nucleus, if it's proportional to 1 over n squared, then as n gets the inner orbits, their n, their integer, have low values. Okay, and the energy at higher, at outer orbits, those n's are larger, right? So if you're squaring it, 1 over n squared, so the outer orbits, their 1 over n squared will be a small value, and the inner orbits, because the n is smaller, their energy levels proportional to 1 over n squared will be larger, right? So, well, in fact, it's sort of minus, so you've got sort of negative energies in a manner of speaking. But don't worry too much about the math. Just get the concept. Bohr's model, as an electron jumps from an outer orbit to an inner orbit, the energy of the inner orbit will be lower, is less than the energy that it had in an outer orbit. So as the electron jumps from an outer orbit to an inner orbit, jumps from outer to inner, it now has a lower energy on the inner orbit. Now energy is conserved, so the outer energy minus the inner energy, that energy difference, where does it go? Well, Bohr's answer was that energy becomes the energy of a photon, and the photon shoots off. Okay? So you've got this kind of formula. So the energy of the photon, so HF, that he just took from Planck and Einstein. So the energy of the photon is is the difference between the energy of the two orbits, the electron orbits. So this would be N1. That's the inner orbit. Is that right? No, the outer orbit minus the inner orbit. Okay. So you get these kind of quantum leaps. So here I've tried to. I don't know if you can see it clearly enough, but here's the nucleus. Here's an inner orbit at energy E1, and here's an outer orbit, energy E2. And if the electron jumps from the outer orbit to the inner orbit, this lower energy here, what happens to the missing energy? Well, a photon gets generated and shoots off, and the energy of the photon will be proportional to frequency. That's Einstein's idea, HF, right? So the energy of the photon is proportional to the difference in energy levels of the orbits. So you're now starting to get a sort of picture of what's going on within the atom. Quantum mechanics is starting to answer some of these questions. Now, really interestingly, with this model, Bohr was saying, well, look, the light that comes out, the frequency here, that will depend on the energy levels of the orbits. Now, you have different atoms, you'll have different energy levels, right? And hence the photon energies, HF, that come out will depend on these energy levels, which depend on the different kinds of atoms. You have different atoms, you'll have, the nuclei will probably be different. Okay, so Bohr was able to explain the light that comes out of different atoms, and he's famous for that. Right, it was a major breakthrough because prior to that, the so-called spectral lines, the frequencies of the light coming out when you heat certain atoms, certain elements, right? That was a mystery before Bohr, but Bohr explained it in terms of his model of the atom in this concept of quantum leaps, right? Well, I've already spoken at length. I've run out of board, so we'll continue on the next session with talking in a bit more detail Heisenberg's uncertainty principle. I'll be sending electrons through a double slit, talking about making it sound even more mysterious, the complementary nature, particle and wave properties of quantum systems. I'll make it sound even more mysterious. We'll do that next session. So, before I sign off, I hope I've given you a sense of both the fascination and the weirdness of quantum mechanics. But let me say this: quantum mechanics is, in a sense, the most fantastically accurate theory in human history. There are certain aspects of quantum mechanics, quantum theory, where the theoretical prediction of a certain quantity is so fantastically accurate. It's accurate to about 1 part in 10 decimal places. It's 1 part in 10 billion, right? And the experimental confirmation is there. Certain things measured extremely accurately to within an accuracy of about 1 part in 10 billion experimentally, and the theory agrees. So no other theory other than quantum mechanics has ever come to such a degree of precision. So obviously something that is being done correctly in quantum mechanics to be able to predict something with such fantastic accuracy in some sense. Now you're probably saying, well, doesn't that sound contradictory with the notion of indeterminism and so forth? Well, it depends. Some things you can measure very accurately. Other things, if you're measuring like 2 things, sometimes you can't measure both very accurately. That's a consequence of Heisenberg's uncertainty principle. Let me finish off by saying the following. Quantum mechanics, the people who do quantum mechanics, they are generally agreed that the formalism, the mathematical models, the math, the tools, there's a pretty strong consensus that works. So people don't question the formalism too much. That's one side of quantum mechanics. But there's no real agreement at all. In fact, a lot of disagreement, and that disagreement's been around for a century now, ever since quantum mechanics got going, on the interpretation of quantum mechanics. There are various schools of thought. There's this interpretation, and there's that interpretation, and another, and another, and another, and many of them. Like I say, I have six shelves, a whole bookcase on books on the interpretation of quantum mechanics. So it's a big topic, and one I'll give you lectures on, certainly in a string of courses in the future, if I can stay alive long enough to do all this work. So summarizing, formalism, pretty much a consensus. Interpretation of the formalism, no agreement whatever, just highly controversial, and it's been that way for a century and it hasn't stopped. You can put 2 quantum mechanics together, and one favorite interpretation is school A, and the other quantum mechanic, his favorite interpretation is from school B, and they'll just be at loggerheads. And that's normal for quantum mechanics. There's no consensus with interpretation, and I'll stop there.